The Earth is speeding up. That sentence should not be possible. For billions of years this planet has been gradually slowing down, tidal drag from the Moon, acting like a brake on every rotation. Then around 2016, something reversed that trend. Days started getting shorter, records started falling 2022, shorter. Nobody fully knows why. What we do know involves liquid iron surging miles underground, ice sheets physically reshuffling the planet's weight, and a magnetic field weakening in ways that haven't been seen in recorded history. We're going to cover all of it. Subscribe so you don't miss what comes next. Something has shifted beneath your feet. Not in a way you can feel, no tremor, no tilt, no warning, but in a way that instruments have been quietly measuring for years. The planet you are standing on is spinning faster than it has at any point in the last half-century of precise scientific observation. Days are getting shorter, not by minutes, not even by full seconds, but by fractions of a millisecond that add up in ways the world's most critical infrastructure was never designed to handle. Atomic clocks are drifting, satellites are registering anomalies, scientists have confirmed the trend, and the forces behind it stretch from the frozen poles all the way to a churning ocean of liquid metal, buried more than 2,000 miles beneath the ground you walk on every day. This is not a single cause story. There is no one lever being pulled, no single culprit to point at. What is happening involves the planet's core, its ice sheets, its magnetic field, its atmosphere, and the deep circulatory systems of its oceans, all of them shifting at once. All of them connected in ways researchers are still working to fully map. Each piece of this puzzle is verified independently. Each has its own body of published science, its own instruments, its own decades of data. What makes the current moment unusual is that so many of them are changing in the same direction at the same time. On the 29th of June in 2022, something slipped into the record books without much fanfare. Earth finished one complete rotation faster than it ever had since scientists began using atomic precision to track such things. The day ran short by 159 milliseconds. Read that number again. A millisecond and a half, for most purposes. That quantity is functionally invisible. You could not notice it. Your body would not register it. Nothing in your daily routine would shift. But scientists do not look at that number and shrug. They look at it and ask why. And when they look further and see that it did not happen just once, that 2020 broke the record, 2021 came close again, and 2022 shattered it. The question stops being whether something real is happening and becomes about what exactly is driving it. The baseline for Earth's rotation, the long-term expected trajectory, has been a gradual slowdown. The Moon has been pulling on the oceans for billions of years, and that tidal drag acts as a brake on the planet's spin. Over enormous spans of geological time, the days have been getting longer. Fossil coral from 400 million years ago preserves daily growth rings that researchers can count. And those rings tell us the year once held more than 400 days. Ancient mud deposits laid down by tidal rhythms confirm it. And the planet was faster then, and it has been winding down ever since. That is the expected story, the direction of travel that the physics predicts. So when around 2016 researchers noticed the trend reversing, when the averages started falling instead of rising, it stopped them cold. The forces that caused the slowdown have not disappeared. Tidal friction is still operating. The Moon is still out there pulling. Something else is now pushing hard enough against that friction to overcome it and produce the opposite effect. That is the puzzle that leads researchers into some of the most extreme environments on or in the planet. places no human has ever reached and no instrument has ever survived long enough to directly sample. To understand the full picture, you have to follow the signal from the surface down, through thousands of miles of rock and metal, and also outward to the edges of the ice sheets and upward into the churning atmosphere. The story of why this planet is spinning faster touches all of it. What makes this matter beyond academic curiosity is infrastructure. The systems that keep modern civilization synchronized, the ones that tell aircraft where they are, that route financial transactions, that balance electricity loads across continents, were calibrated for a planet behaving a certain way. They were built with tolerances and margins that assumed Earth would behave within a certain range. The planet has moved outside that range, and the engineers maintaining those systems are working harder than ever to keep up. One particular technical crisis is approaching that most people have never heard of: the possibility of removing a second from the official global clock, a step that experts have described in published papers as potentially catastrophic for digital infrastructure worldwide. That is where this story is heading, and it starts with the most accurate timekeeping device ever built. Before 1955, the most accurate clocks available were mechanical instruments that might lose or gain a second every 300 years. That sounds remarkable until you understand what precision actually requires when you are trying to measure a planet. Scientists studying Earth's rotation needed something better. They needed a clock that did not drift, a reference so stable that any change in its reading could be attributed entirely to the thing being measured, rather than the thing doing the measuring. The atomic clock gave them exactly that. Its principle is deceptively simple. Certain atoms vibrate at a frequency so consistent that it can serve as the definition of a second. Cesium-133, the element used in the most precise versions, oscillates more than 9 billion times per second. Every single oscillation, every single time, without exception. The resulting instrument is so reliable that it would neither gain nor lose a second over a span of 300 million years. With that level of accuracy suddenly available, researchers could point it at the planet and finally hear the noise in the signal. What they found was that Earth was a terrible timekeeper. The rotation fluctuated constantly. It sped up slightly in the northern hemisphere's winter as atmospheric mass shifted toward the poles. It slowed a little in summer. Major earthquakes left faint marks in the data. Ocean circulation patterns applied their own subtle push and pull. Even large amounts of snow piling up at high latitudes produced a measurable signature. None of this was random noise. All of it had physical explanations. But it meant the planet was constantly wobbling around its average rate, rather than holding steady. Researchers cataloged these variations and accounted for them. The system worked. The measurements were coherent, and the long-term trend of gradual deceleration was confirmed with precision that pre-atomic clocks could never have achieved. Then the data from 2016 onward began to tell a different story. The fluctuations were still there, layered on top of each other the way they always had been, but underneath them something new was emerging. The average length of a day, filtered clear of seasonal noise and known cyclical effects, was trending shorter. Year after year, the filtered average was falling. This was not a blip. It was not a seasonal artifact that would correct itself in 6 months. It looked, unmistakably, like a trend. The International Earth Rotation and Reference System Service, the Paris-based organization that monitors this globally and coordinates data from stations on every continent, ran every check available. They cross-referenced readings from atomic clock networks in different countries. They verified instrument calibration. They reprocessed the data using independent methods. The instruments were fine. The signal was real. Here is the detail that made researchers stop mid-sentence. Even after subtracting every known contributing factor, a residual remained. Tidal friction was accounted for. Seasonal atmospheric effects were removed. Known ocean circulation patterns were factored out. After all of that, something was still pushing the planet faster than the models expected. They had a clean, verified measurement of acceleration with no complete explanation in hand. That situation, a confirmed anomaly without a full cause, is exactly the kind of thing that drives science forward into uncomfortable territory. Because when they went looking for what might explain the leftover signal, they did not find it in the atmosphere, or the oceans, or the ice. They found it, or at least the strongest candidate for it, in a place that is genuinely difficult to picture. A churning ocean of liquid iron buried deep inside the planet, in total darkness, under pressure that would crush any known material to powder. The leap second is the mechanism that the world built to deal with Earth's unreliable rotation. Introduced in 1972, it was a patch, a practical engineering solution to a mismatch between two different ways of measuring time. Atomic time is anchored to physics, to the vibration of cesium atoms, and it runs perfectly steady. Solar time is anchored to the planet, to the rhythm of day and night, and it fluctuates. For most practical purposes, for navigation, for communication, for keeping noon aligned with midday, these two timescales need to stay roughly in sync. The leap second was the mechanism for doing that. Whenever the gap between atomic time and Earth time grew large enough, timekeeping authorities would add a single extra second to the official clock. In more than 50 years of this system, 27 extra seconds have been inserted. Not one has ever been removed. The planet was always slowing, atomic clocks always ran ahead, and the fix was always to add time. Now the situation has reversed. And the conversation that was unthinkable for decades is suddenly unavoidable. The negative leap second is something most people have never heard of, and almost no engineer wants to implement. When the planet was gradually slowing, the leap second was a simple addition, an extra heartbeat inserted into the official clock once or twice a year. Clocks ticking from 2030 59 and 59 to 2030 59. 60 before rolling over to midnight. Awkward for software, but manageable. In 2012, when a positive leap second was applied, servers at Reddit, LinkedIn, and Qantas Airlines crashed simultaneously. Engineers spent hours tracing what turned out to be a single added second interacting poorly with certain scheduling software. That was a positive leap second, time moving forward, adding something familiar. A negative leap second is the opposite. Clocks would jump from 2039:58 directly to midnight. 2039:59 would simply not exist. Every process, every log entry, every financial transaction, every database record time to that missing second would encounter a gap, a hole in time. Engineers at Meta, the company that operates Facebook and Instagram, published a technical paper that described the possible consequences in plain terms. They called the negative leap second an event with a devastating potential effect on software that relies on timers or scheduling. Their recommendation was not to apply one at all. Instead, they proposed smearing, spreading the correction across a longer window so that no single moment ever experiences an abrupt discontinuity. Over 12 hours, for instance, each clock tick would be made very slightly shorter or longer, so the total adjustment accumulates gradually rather than landing all at once. The problem is that different organizations implement smearing differently. Google, Amazon, and Microsoft all developed their own approaches. During the smearing window, two systems comparing timestamps would be operating in subtly different versions of time. For most applications, the difference would be negligible. For some, it would not. High-frequency financial trading is among the most sensitive. Stock exchanges execute millions of transactions per second, each one carrying a timestamp that determines its place in the sequence. Order books match buyers to sellers based strictly on the order in which bids arrive. If one exchange's clock shifts while another's does not, even by a fraction of a second, the sequence of trades becomes ambiguous. Transactions that appeared settled become disputed. Trades placed after the subtracted second might be logged as having occurred before trades placed before it. Regulatory frameworks require financial institutions in some jurisdictions to maintain records accurate to the microsecond. A 1-second backward jump does not just create accounting confusion. It creates legal liability that must be audited and resolved manually. Power grids face a related but distinct version of the problem. Electricity flows across interconnected regional networks at a fixed frequency, 50 cycles per second in most of the world, 60 in North America. Grid operators synchronize their systems to coordinated universal time to balance load across the boundaries between regions. When time drifts, load balancing drifts with it. A sudden discontinuity in the timekeeping signal creates a window where the coordination that keeps the system in phase breaks down. In most cases, automated protective systems compensate within seconds. But in the industry, there is a term for that gap, a synchronization event, and synchronization events are the precursor to the kind of cascading failures that pull large sections of a grid offline. Aviation presents yet another layer. Air traffic control depends on synchronized timestamps to track aircraft and resolve potential conflicts between flight paths. When controllers at different facilities work from clocks that briefly disagree, the margin built into separation standards gets consumed by the ambiguity. The tolerances in modern instrument approach procedures, the ones that guide aircraft to within feet of a runway in zero visibility, depend on satellite positioning systems that are themselves synchronized to the same global timescale. A discontinuity at the base of that synchronization chain propagates upward through every system that depends on it. In 2022, an international standards body voted to eliminate the leap second entirely by 2035, allowing the gap between atomic and Earth time to accumulate until a different correction mechanism can be designed. But that decision does not make the problem go away. It defers it while the underlying mismatch keeps growing, and the deeper force driving that mismatch has its origin somewhere that no policy decision can reach. Every time you ask your phone where you are, a quiet negotiation takes place between your device and a constellation of satellites orbiting more than 12,000 miles overhead. Those satellites do one thing with extraordinary precision: they broadcast a timestamp. Your phone receives signals from at least 4 of them, compares the tiny differences in when each signal arrives, and uses those differences to calculate your position to within a few meters. The entire system depends on one foundational assumption: that the satellites know where Earth is. Not approximately, not within a city block, down to the centimeter, in real time, continuously. Each satellite in the GPS constellation carries multiple atomic clocks and follows a precisely calculated orbital path. Ground stations track those orbits constantly and send correction data upward to keep the satellites' position models accurate. The satellites in turn hold a continuously updated model of where the surface of Earth should be at any given microsecond, based on the planet's expected rotation rate. When Earth spins faster than expected, the surface moves ahead of the prediction. The error is small in isolation, depending on the degree of mismatch. It might translate to a positional discrepancy of a few centimeters to a few meters. But that range spans the difference between acceptable and unacceptable, depending entirely on the application. A family using navigation to find a coffee shop has a tolerance of roughly a city block. A cargo vessel navigating a narrow channel at night has a tolerance of about a ship width. A precision agricultural machine guided by GPS has a tolerance of centimeters. A surveying team boring a tunnel from both ends simultaneously has essentially no tolerance at all. Ground control teams compensate for Earth's rotational variations continuously. It is not a new challenge, and the correction systems have real margins built in. But the corrections are not applied instantaneously, they come in periodic updates. And between updates the system operates on its last known model of Earth's behavior. When the planet accelerates in ways that outpace those updates, there is a window where the model is running behind reality. The larger and faster the acceleration, the wider that window. And the larger the potential positional error, at the moment a user most needs the system to be right. The situation is further complicated by the fact that GPS is not the only positioning system in the sky. Russia operates GNOS. The European Union operates Galileo. China operates Beidou. Each uses its own atomic clocks and its own ground correction network. They are all coordinated to the same underlying time standard. But they update at different intervals, and their correction models do not always agree. Under normal conditions, the disagreements between systems are negligible. Devices that blend signals from multiple constellations to improve accuracy receive essentially identical results regardless of which combination they use. But when Earth accelerates in ways that push against all of the correction models simultaneously, the systems can begin to diverge. Devices receiving contradictory position data from different constellations have to choose how to resolve the conflict. In most cases, averaging works fine. In edge cases, the very situations where precision matters most, it does not. Aviation regulators have already issued technical bulletins acknowledging that increasing anomalies in timing and geophysical behavior require more frequent updates to navigation databases. The standard update cycle for aviation navigation data has historically run on a 28-day schedule. Certain categories of data are now being flagged for review on shorter timelines. This is not a declaration of crisis. The systems remain robust, and the engineers maintaining them are skilled and attentive. But there is a meaningful difference between a system that runs well within its design parameters and one that is being pushed toward the edges of those parameters. The monitoring teams responsible for GPS, GLONASS, Galileo, and Beidou are working harder than they were a decade ago. And the reason is a planet that has started behaving differently from the baseline their instruments were calibrated against. If you could somehow travel straight down through the ground beneath your feet, through the crust, through miles of rock, through the upper and lower mantle, past the point where pressure becomes so extreme that atoms are forced into arrangements that simply do not occur at the surface, you would eventually arrive at the outer core. It begins about 1,800 miles down and extends another 1,400 miles inward. It is made primarily of iron and nickel. It is hotter than the surface of the sun. And despite those temperatures, which by any ordinary chemistry should produce a liquid, the outer core is not solid, it flows, it churns. It moves in vast slow currents driven by the temperature difference between the cooler base of the mantle above and the intense heat radiating outward from the solid inner core below. These currents are not slow in any meaningful human sense. On geological timescales they move with surprising speed, tens of miles per year in some estimates, and because they consist of electrically conductive liquid metal, they generate something. Flowing liquid iron in the presence of magnetic fields creates electrical currents. Those electrical currents in turn reinforce the magnetic field. The process feeds on itself in a self-sustaining loop called the geodynamo. The result is the magnetic field that extends outward from the core, through the mantle, through the crust, and out into space for tens of thousands of miles. That field is the reason charged particles from the sun do not strip away the atmosphere. It is the reason life on the surface is possible at all. In this very direct sense, what is happening in the outer core is not a remote geological curiosity, it is the mechanism that keeps this planet habitable. But the outer core does more than generate the field. It physically interacts with the rotation of everything above it. The outer core does not spin at exactly the same rate as the overlying mantle and crust. There is a coupling between the layers, transmitted through pressure and electromagnetic forces, but the core retains some rotational independence. When the flow patterns inside it shift, when the massive rising and sinking columns of iron that make up its circulation change direction or speed, they exert a torque on the layer above. That torque is not hypothetical, it is measurable in the rotation data. Researchers who have spent careers correlating changes in Earth's magnetic field with changes in the rotation rate have found a consistent pattern. When the field shifts in certain ways, the rotation tends to change. The coupling mechanism is still being refined, but the correlation is strong enough that geophysicists now treat core dynamics as a primary driver of rotation variations on decadal timescales. The acceleration that began showing up clearly in the surface data around 2016 coincides with changes in the outer core's circulation pattern that were independently detected in satellite magnetic field data. The timing is not coincidental. The data from two completely separate measurement systems, one tracking the planet's spin rate from the orientation of distant quasars, another tracking magnetic field strength from instruments in low Earth orbit, points to the same origin in the same time window. And wrapped at the center of all this, inside the liquid iron outer core, is something that makes the picture stranger still. A solid ball of iron roughly the size of the moon, spinning inside the liquid ocean, inside the mantle, inside the crust, inside the thin layer of air and water and rock where you exist. And that innermost sphere has recently done something nobody predicted. At the very center of Earth, about 3,600 miles beneath your feet, there is a sphere of solid iron wider than the moon. The fact that it is solid at all requires explanation. The temperature at that depth is somewhere around 9,000 degrees Fahrenheit, comparable to the outer layers of the sun. At that temperature, iron should not be solid. At that temperature, almost nothing should be solid. But at the center of a planet, temperature is not the only variable in play. Pressure is. The entire weight of the Earth, every mile of rock and metal above it, presses inward with force so enormous that it overrides the thermal energy, trying to shake atoms apart. The iron atoms at the center are packed so tightly that no amount of heat can break them free of their crystalline arrangement. The result is a solid ball embedded in a liquid ocean, floating without touching the surrounding walls. Coupled to the layers above it, only through the medium of the flowing outer core. Because the inner core has no rigid connection to the mantle or crust, it can rotate independently. For decades, geophysicists suspected this was the case, but had no direct way to confirm it. The confirmation came from an unusual direction: earthquakes. When a major earthquake occurs, it sends seismic waves radiating outward in every direction, including straight down through the center of the planet and up the other side. Sensitive instruments positioned around the world record these waves, and the time it takes for a wave to travel through different materials reveals something about what those materials are and how they are arranged. The inner core's crystal structure is not perfectly uniform. It transmits seismic waves faster along certain orientations than others. By comparing recordings from similar earthquakes over decades, researchers found that wave travel times through the inner core were slowly changing. The most straightforward explanation was that the inner core was rotating, gradually shifting the orientation of its crystal lattice relative to the paths the waves were traveling. This was confirmed through the late 20th century. The inner core was rotating slightly faster than the mantle above it, not dramatically, not in a way you could ever detect at the surface, but measurably, consistently, year after year in the seismic record. Then a study published in the journal Nature Geoscience in 2023 drew a more disquieting conclusion from a longer dataset. The inner core's faster rotation had been slowing. By around 2009, according to the analysis, it had matched the rotation rate of the mantle. And sometime after that, around 2010 to 2012, it appeared to go further, rotating slightly slower than the mantle above it. The implication, drawn from decades of seismic wave travel times, was that the inner core had reversed its rotation relative to the surface. It was now turning in the opposite direction from the planet surrounding it. Sit with that for a moment. The solid iron center of the planet, the innermost sphere inside the liquid ocean, inside the rocky mantle, inside the crust you stand on, may now be rotating in the opposite direction from everything outside it. The forces involved are not trivial. The angular momentum of the inner core is substantial, and when its rotation changes, that angular momentum does not simply vanish. It transfers outward through the liquid outer core, which transfers it to the mantle, which transfers it to the crust. Each transfer involves a delay, a coupling loss, a conversion of rotational energy that propagates upward through the layers over years to decades. Some researchers believe this upward transfer of angular momentum is a direct contributor to the surface acceleration that began showing up in the data around 2016. The lag between the inner core's apparent behavioral change in the early 2010s and the measurable surface effect several years later fits the estimated timescales for coupling through the outer core and mantle. The 2023 study claiming inner core reversal is not universally accepted, and understanding why requires understanding what the evidence actually consists of. There are no drilling instruments that have reached the inner core. There are no direct measurements of any kind from that depth. Everything researchers know about the planet's interior comes from seismic waves, vibrations generated by earthquakes and nuclear tests and other disturbances that travel through the Earth and emerge on the other side where instruments can record them. The inner core's crystal structure affects those waves in subtle but detectable ways, and by analyzing how those effects have changed over time, scientists infer changes in the core's orientation, and therefore its rotation. This is indirect evidence. It is carefully analyzed, painstakingly cross-referenced, and published after extensive review. But it is still inference from a signal rather than direct observation. Critics of the reversal interpretation point out that alternative explanations exist. The surface of the inner core is not perfectly smooth. It has topographic variations, ridges and valleys of iron crystal that could scatter seismic waves differently as conditions change, without requiring any rotation at all. Changes in the structure of the overlying liquid outer core could also affect wave travel times. A wave that passes through the outer core on its way to the inner core and back out again is subject to whatever is happening in that liquid layer, and the outer core is known to be changing. Attributing the signal purely to inner core rotation requires ruling out all these alternatives, and critics argue that has not been done definitively. What both sides of the debate agree on is the most important part. Something changed inside the planet during the first decade of this century, and the behavior of the inner core in the 21st century is different from its behavior in the 20th. That much is not disputed. The argument is about what the change was, and even if you accept the more conservative interpretation, that the inner core simply slowed its over-rotation and matched the mantle without actually reversing, the rotational implications are still significant. Angular momentum that was being stored in the faster, spinning inner core is now being redistributed. The question is where it went, and the answer the physics points to is upward, through the layers, toward the surface. The timeline supports this. The inner core's apparent deceleration, by most estimates, was underway in the late 2000s and early 2010s. The surface acceleration became clearly measurable in the data by around 2016 and intensified through 2020 and 2022. The gap between those two windows, roughly 5 to 10 years, is consistent with estimates of how long it takes rotational changes at the center to propagate through the outer core and mantle, before showing up as a surface effect. If the transfer is still ongoing, if the inner core is still shedding angular momentum upward, then the surface acceleration has more energy behind it, and if the inner core eventually reaches a new stable rotation rate, or if it has already reversed and is now re-accelerating in the other direction, the surface will feel that too, with the same lag. The center of the planet is communicating with the surface. We are reading the messages with atomic clocks, and the signal says something changed. The figure skater on a spinning stool is the most popular metaphor in Earth rotation science, and it is popular because it actually captures something true. A skater who extends their arms slows down. A skater who pulls them in speeds up. No external force is applied. No energy is added or removed. The only thing that changes is how the mass is distributed relative to the rotation axis. The physics that governs this, conservation of angular momentum, is the same physics that connects melting ice sheets to the spin rate of a 4.5 billion-year-old planet. For most of the last 20,000 years, enormous ice sheets covered large portions of the northern hemisphere. These sheets were concentrated near the poles, which means their mass was sitting close to Earth's rotation axis. When glaciers melt, that water does not stay near the poles. It flows into the ocean and spreads toward lower latitudes, moving mass away from the axis. Moving mass away from the rotation axis increases the moment of inertia, the rotational equivalent of extending the arms, and by conservation of angular momentum, the spin rate must decrease to compensate. This is the post-glacial rebound effect, and it has been contributing to Earth's gradual deceleration for thousands of years. In the long run, it points toward a slower planet. But here is the short-term complication. The ice sheets are losing mass faster than any model predicted even a decade ago. Greenland is now shedding roughly 280 billion metric tons of ice per year. Antarctica is losing approximately 150 billion metric tons annually. These are not estimates based on projections. They are direct measurements from the GRACE and GRASS follow on satellites, which track tiny variations in Earth's gravitational field by measuring the distance between two satellites flying in formation. When mass shifts on the surface, the gravitational field shifts, and the satellites drift fractionally closer together or further apart. Using that data, researchers have mapped the redistribution of planetary mass in real time, and the picture is unambiguous. The poles are losing mass and the mid-latitude ocean basins are gaining it. The redistribution is not uniform, and its rotational effects are not simple. Different regions of the ice sheet melt at different rates. Different ocean basins accumulate water at different depths and latitudes. The interaction between where mass is going and how that interacts with Earth's three-dimensional shape produces effects that cannot be calculated by simply adding up the contributions. One of those effects is that the planet's actual spin axis, not the magnetic pole, but the geometric axis around which everything rotates, has physically shifted by a measurable amount over the past 2 decades. This is not a predicted consequence of a model. It is a confirmed measurement. The axis has moved in a direction that aligns with the pattern of ice loss from Greenland and West Antarctica. Scientists have also observed that the rate of this polar drift accelerated sharply around the year 2000, coinciding almost precisely with the onset of accelerated Greenland ice loss. The mass leaving the poles is not just changing the spin rate, it is moving the axis itself. Earth does not spin on a perfectly fixed axis. It wobbles. It has always wobbled, multiple overlapping motions, each with its own period and cause, combining into a complex drift of the geographic poles across the Arctic surface. Scientists have been tracking this drift since the late 19th century, and for most of that time the drift had a consistent direction. The geographic North Pole moved slowly toward northern Canada at a rate of a few centimeters per year. The cause was well understood. The crust and mantle were still slowly rebounding from the weight of the ice sheets that blanketed North America and northern Europe during the last ice age. As the planet gradually adjusted to their removal, the pole drifted in the direction the physics predicted. Then around the year 2000, the direction changed. The pole turned eastward, toward Greenland. The rate of drift increased substantially, from a few centimeters per year to roughly 17 centimeters per year over the following 2 decades. When researchers analyzed the cause using data from the Dryas satellites, the answer came back clearly. The primary driver was accelerating ice loss from Greenland. Greenland sits in a specific location relative to the drift trajectory, and as its ice sheet loses mass, it pulls the planetary axis toward it through the mechanics of mass redistribution. The correspondence between the onset of accelerated Greenland melting and the turn in polar drift direction is close enough that scientists treat them as directly linked. West Antarctic ice loss has also contributed, pulling in a slightly different direction and adding to the net eastward trend. The consequence is that the actual geographic pole, the point on the surface directly above Earth's rotation axis, is now located somewhere measurably different from where it was a generation ago. This is not a dramatic shift by any visual or experiential standard. It would not change where you see the North Star from your backyard, at least not on any human timescale. But at the level of precision required by satellite navigation systems, geodetic surveys, and global timekeeping infrastructure, it matters enormously. Every system that uses the precise location of Earth's rotation axis in its calculations has to be updated regularly to account for the drift. The International Earth Rotation and Reference System Service publishes updated Earth orientation parameters every few days, and those parameters feed directly into the correction models used by every major satellite navigation constellation. The updates have been coming with increasing frequency, as the drift accelerates. There is a second motion layered on top of the polar drift that has also been behaving unusually. Earth has a rhythmic rocking called the Chandler wobble, a roughly 14-month cycle in the geographic pole's position caused by the fact that the planet is not a perfect sphere. A non-spherical rotating object wobbles around its geometric axis the way a football wobbles as it spirals through the air. For a rigid body, this wobble would damp out over time due to friction. Earth is not rigid. The crust flexes, the mantle flows, the oceans slosh, and those flexibilities continuously re-excite the wobble, keeping it going. For decades, the Chandler wobble was one of the most predictable features of Earth's rotation behavior. Then around the year 2000, its amplitude began to shrink. By around 2005 or 2006, it had dropped to roughly a fifth of its typical size. It had nearly vanished. The leading explanation was a shift in where cold, dense water sinks to the ocean floor. A change in deep ocean circulation substantial enough to suppress a fundamental feature of planetary rotation. A force as persistent as the Chandler wobble had been dampened by changes in the ocean. The wobble eventually recovered, but the episode was a warning about how sensitive these deep rotational features are to changes happening on and near the surface. The water that was once frozen in Greenland and Antarctica does not disappear when it melts. It enters the ocean, and the ocean is not a uniform container. It has basins of different depths, ridges and trenches that direct flow, and a rotation, the planet's own rotation, that influences how water distributes itself across those basins. The result is something that surprises almost everyone when they first encounter it. Sea level rise is not uniform. It does not fill the ocean the way you would fill a bathtub. Near a large ice sheet, sea level actually drops when the ice melts. The ice sheet is so massive that its gravitational attraction pulls ocean water toward it. When the ice disappears, that gravitational pull weakens, and the water that was drawn toward the poles spreads outward toward lower latitudes. Coastlines near Greenland experience a modest sea level decrease as Greenland loses ice. Coastlines in the tropics and the southern hemisphere experience disproportionately large rises, more than the global average would suggest, precisely because they are the destinations for the water that was pulled poleward by the ice that no longer exists. This redistribution carries rotational consequences. Moving mass from high latitudes to lower latitudes increases the distance of that mass from the rotation axis. By conservation of angular momentum, this should slow the rotation. In the long term, as more ice melts and more water accumulates in low-latitude ocean basins, this effect will produce a measurable deceleration. But in the short term, during the transition, the redistribution is happening simultaneously across multiple regions at different rates with different rotational signatures. Greenland melts faster in summer. Antarctic glaciers calve throughout the year. Monsoon patterns and El Niño cycles move water between basins seasonally. The net rotational effect at any given moment is the sum of all of these contributions, and it oscillates even as its long-term average moves in one direction. This oscillation makes it difficult to cleanly separate the ice contribution from background noise in the rotation data, which is part of why researchers cannot yet point to a single dominant cause and say definitively, this is what is driving the acceleration. What they can say is that the ocean mass redistribution is measurable from space. It is changing the planet's moment of inertia in real time, and the rate of change is faster than models predicted 20 years ago. The planet is not just spinning at an unusual rate, its weight distribution is shifting. And a spinning object whose weight distribution shifts does not just change speed. It changes the character of its wobble, the stability of its axis, and the way it responds to other forces acting on it. Some of those other forces are coming from the atmosphere, which weighs more than 11 quadrillion pounds, and is in constant motion, pushing on the rotating surface beneath it with forces that are small on a per square meter basis, but enormous in aggregate. The atmosphere is not light. It does not float passively above the surface like a decorative layer of gas. It is a layer of matter with real mass, roughly 5 quintillion kilograms in total, and when that mass moves, it pushes. The connection between atmospheric motion and Earth's rotation rate is not a theoretical abstraction. It is measured directly and continuously by teams that track what is called atmospheric angular momentum. When the atmosphere gains angular momentum, typically through the amplification of large-scale wind systems, the solid Earth slows down slightly to conserve the total. When the atmosphere loses angular momentum, the solid Earth speeds up. The exchange is continuous, and it is one of the dominant sources of the short-term noise visible in rotation data. The dominant seasonal signal is caused by the jet stream. The winter hemisphere develops stronger west to east winds that carry angular momentum. The solid Earth responds by rotating slightly more slowly in the northern hemisphere's winter than in its summer. The effect is measurable at the precision of modern atomic clocks, on the order of about 1 millisecond variation across the year. But there are non-seasonal components as well, and the most significant of these is El Nino. During a strong El Nino event, the trade winds that normally blow steadily across the tropical Pacific weaken. The atmosphere transfers angular momentum to the ocean, and the coupling from the ocean to the solid Earth produces a detectable change in rotation rate. The strong El Nino events of 1982 to 1983, 1997 to 1998, and 2015 to 2016 each produced measurable rotation anomalies. The 2015 to 2016 event was one of the strongest on record, and it coincides with the beginning of the surface acceleration trend that researchers have been tracking ever since. That does not mean El Nino caused the acceleration. The trend has persisted well beyond any El Nino's influence, and its magnitude is larger than El Nino alone can account for. But El Nino may have contributed an initial push that other forces, core dynamics, ice redistribution, ocean circulation changes, then extended and amplified. The atmosphere, in this picture, is not a cause so much as an amplifier and a connector. It receives signals from ice loss, from ocean warming, from magnetic field changes through effects on ionospheric circulation, and it rebroadcasts them as mechanical forces on the crust below. A shifting jet stream pattern, which has been well documented over the past 2 decades, and is linked to the shrinking of Arctic sea ice, changes how atmospheric angular momentum distributes across latitudes. The stratospheric polar vortex, when it disrupts and breaks down, spills cold air equatorward in a way that redistributes atmospheric mass and creates a brief, but measurable rotational pulse. The atmosphere also responds to changes in ocean circulation in ways that feed back into the rotation. A warming ocean drives more intense tropical storms. A major hurricane is a rotating atmospheric structure that concentrates angular momentum in a small area. Its formation and decay redistributes angular momentum between the atmosphere and the ocean in ways that carry a rotational signal. An ocean that generates more intense storms more frequently is an ocean that perturbs the rotation budget more often. None of these individual effects is large enough to be the dominant driver of what is currently happening, but each is real, measurable, and connected to the others. The atmosphere, in this sense, is an integrating layer. It receives energy and information from every other system on the planet, and converts it all into mechanical force on the rotating surface. The deep ocean moves slowly, its great circulatory systems, the networks of currents driven by differences in temperature and salinity that carry water through every ocean basin on timescales of centuries, are not headlines the way hurricanes are. They do not have names. They do not make landfall. But they move more water than all the rivers on Earth combined, and they carry angular momentum. When they change, the planet feels it. The Atlantic meridional overturning circulation is the component of this system that draws the most scientific attention. It carries warm surface water northward along the eastern coast of North America and toward Europe, then sinks as it cools and becomes denser and returns southward as a cold, deep current. It is the engine behind the relatively mild climate of northern Europe and much of the heat exchange between tropical and polar latitudes in the Atlantic basin. It has been weakening. Multiple independent data sets, sediment records, satellite altimetry, direct current measurements from moored instruments, all point to the same conclusion. The circulation is operating more slowly than it was several decades ago. Some analyses suggest it is now at its weakest point in at least 1,000 years. The rotational implication of a weakening circulation is not straightforward. The circulation transports angular momentum through the ocean basins in a specific pattern, and when the pattern changes, the distribution of ocean angular momentum changes with it. Some components of that change would add to the surface rotation rate, others would subtract. The net effect depends on the details of how the flow reorganizes. What is clearer is the thermodynamic side effect. As the circulation weakens, heat that would normally be transported northward stays in lower latitudes. The upper ocean warms. Warmer water is less dense and occupies more volume. Sea level rises not just because ice melts, but because the water itself expands. The vertical structure of the ocean changes, with the boundary between warm surface water and cold deep water shifting downward. This alters where angular momentum resides within the water column and how it couples to the rotation below. The ocean also affects the Chandler wobble in ways that have become better understood in recent years. The wobble's amplitude, how large the circle it traces at the pole, depends on how well the ocean and atmosphere continuously re-excite it. If ocean circulation changes in ways that alter where and how energy is being deposited into this system, the wobble responds. The near disappearance of the Chandler wobble in the early 2000s, which researchers linked to changes in deep ocean circulation, demonstrated that this connection is not theoretical. A sufficiently large change in where cold, dense water sinks can suppress a rotational feature that had been running steadily for as long as it had been observed. As the Atlantic circulation continues to weaken, its effect on both the rotation rate and the stability of these deeper wobble patterns remains an open question. Earth's magnetic field is not uniform. It wraps the planet unevenly, stronger in some regions and weaker in others, generated by the turbulent and asymmetric flow of liquid iron in the outer core. Most of the regional variations are modest enough that they go unnoticed by anything except sensitive instruments. But one region stands out, and has been standing out with increasing intensity for the past century. Over the South Atlantic Ocean and across much of South America, the field is dramatically weaker than it should be. In the most affected area, the field intensity is roughly 40% below what would be expected at comparable latitudes elsewhere. This is the South Atlantic anomaly, and it is growing. The practical consequence of this weakness becomes apparent at altitude. Earth's magnetic field deflects charged particles from the Sun. The stream of protons and electrons called the solar wind as well as high-energy cosmic rays arriving from beyond the solar system. In most regions, this protection begins at an altitude high enough that satellites in low Earth orbit are shielded. In the South Atlantic anomaly, the field is so weak at lower altitudes that charged particles penetrate further before being turned aside. Satellites passing through this region encounter elevated radiation levels that can cause electronic malfunctions. The International Space Station takes precautions whenever its orbit carries it through the anomaly. Sensitive instruments are powered down. Astronauts are advised to reduce their time in exposed modules. This has been standard practice since the anomaly was first documented in the 1950s. What has changed is that the anomaly is expanding. Its minimum intensity is deepening, and recent data suggests it may be developing a second minimum, splitting into two separate weak zones. The cause lies beneath the anomaly, in the outer core. Under the South Atlantic, there is an unusual structure called a low-velocity zone, where liquid iron behaves differently from the surrounding material. Researchers believe this zone represents a patch of reversed magnetic polarity, an area where the local field alignment is opposite to the global dominant direction. The interaction between this reversed patch and the overall field above produces the weakness at the surface. The patch is not static, it is growing. And this connects to the rotation story in a way that is not immediately obvious, but is physically direct. Changes in outer core flow patterns affect the magnetic field. Changes in the magnetic field affect the electromagnetic coupling between the outer core and the mantle. Changes in that coupling affect how angular momentum transfers between the core and the surface. The South Atlantic anomaly is not just a radiation hazard for passing satellites. It is a visible symptom of the same outer core changes that appear to be linked to the surface acceleration. The two phenomena share an origin, even if they are not the same thing. Magnetic field reversals are one of the stranger confirmed facts in all of Earth science. The polarity of the planet's field has flipped hundreds of times across geological history, north becoming south, south becoming north, with a rough average interval of a few 100,000 years, though the actual timing varies enormously. The most recent full reversal, called the Brunhes-Matsuyama reversal, occurred roughly 780,000 years ago. By average statistics alone, the planet is past due, but the word overdue carries a specific meaning here that deserves careful handling. Reversals do not happen on a clock. The interval between them ranges from tens of thousands to tens of millions of years. Being beyond the average interval is similar to noting that a coin has come up heads 17 times in a row. It tells you that the probability was low, not that the next flip is guaranteed to be different. What the geological record does tell us is that reversal is a normal part of Earth's behavior. Life has survived every reversal across hundreds of millions of years of planetary history. But the word survived is doing real work in that sentence. During a reversal, the field does not flip instantaneously. The transition unfolds over thousands of years, and during that transition the field weakens globally, potentially to 10 or 20% of its normal strength across most of the planet. The protection against charged particles is significantly reduced for a sustained period. The consequences are not extinction level, but they are not trivial either. Cancer rates from elevated radiation reaching the surface would increase. Damage to satellites and power grid infrastructure would intensify. Navigation systems used by migratory animals, birds, sea turtles, certain fish species would be disrupted. Atmospheric chemistry would be altered by increased particle flux. The infrastructure of modern civilization, which depends heavily on satellites that are already showing stress from the current localized weakness in the South Atlantic, would face a far more challenging environment globally. The connection between field reversals and Earth's rotation runs through the geodynamo itself. The convective flows in the outer core that generate the magnetic field are powered by the same processes that interact with the rotation of the mantle above. The field and the rotation are not independent systems operating in parallel. They are coupled. When outer core flow patterns change in ways that weaken the field, those same changes alter the electromagnetic torque on the mantle. That torque affects the surface rotation rate. Researchers studying paleomagnetic records, the preserved field history in ancient basalt, in seafloor sediment cores in cave formations, have found correlations between periods of field weakness and anomalies in the geological record. The relationships are not fully understood, but they appear consistently enough that they cannot be dismissed. What is particularly relevant to the current moment is that the global field has declined by roughly 9% since systematic measurements began in the early 19th century. 9% in roughly 180 years. Whether that represents the beginning of a reversal, a temporary fluctuation, or something in between is not yet determinable. What can be said is that the field is behaving differently than it was 2 centuries ago, and the core driving it is behaving differently than it was 2 decades ago. There is a library inside the planet. Not books, not writing, but physical records laid down in stone at the moment molten rock cooled and locked the prevailing magnetic field direction into the tiny magnetic minerals freezing in place within it. These records are permanent. A basalt formed 600 million years ago carries the field direction of 600 million years ago, preserved without alteration, readable with modern instruments. Using this library, paleomagnetists have reconstructed the history of Earth's magnetic field with remarkable detail extending back more than 4 billion years. The ancient record also captures information about rotation. Thin layers in seafloor sediments preserve cyclic variations tied to tidal rhythms, which in turn encode the number of tidal cycles per year, a quantity directly related to rotation rate. Ancient coral is the most accessible of these recorders. Coral grows in daily and annual increments, and the growth rings can be counted. Specimens from 400 million years ago showed approximately 400 rings per year when first analyzed in the 1960s. Since the orbital year has a fixed duration determined by the planet's path around the Sun, more days in a year means shorter days. The planet was spinning faster. Tidal sediment rhythmites from approximately 620 million years ago suggest days of roughly 21 to 22 hours. The long-term deceleration driven by tidal drag from the Moon is real, confirmed, and written in stone. But within that long deceleration, the record shows variation. Periods where the rate of slowing changed. Periods where small reversals of the trend occurred. The planet's rotation history is not a simple one-way curve. It has fluctuated on timescales from decades to millions of years, driven by the interplay of tidal braking, core dynamics, and mass redistribution. The seafloor itself preserves the reversal history of the magnetic field in parallel stripes of normally and reversely magnetized rock extending outward from mid-ocean ridges. The width of each stripe corresponds to how long the field maintained that polarity before flipping. The record is detailed enough to identify geomagnetic excursions, brief events where the field weakened and began to shift but then recovered without completing a full reversal. The last Champ excursion, roughly 42,000 years ago, is the most studied of these. During that event, global field intensity dropped dramatically over several centuries, then recovered over several thousand years. Evidence in cave formations, ice cores, and tree rings from that period suggests elevated cosmic ray flux during the excursion. Some researchers have connected it to periods of accelerated climate change and megafauna extinction, though the causal relationships remain debated. The point is not that another last-scale event is imminent. The point is that these events have happened. They left measurable signatures in the biological and geological record, and the current state of the magnetic field has measurable similarities to early-stage excursion behavior. The ancient record does not predict the future, but it defines the range of what is possible, and it shows that the extremes are more extreme than intuition suggests. When researchers look back at Earth's rotation history and search for the last period that resembles what is currently being measured, the best match is not a random fluctuation in the middle of a quiet era. It is the end of the last glacial maximum, the period roughly 15,000 to 20,000 years ago, when the ice sheets that had blanketed large portions of the northern hemisphere began their final collapse. As those sheets broke apart, enormous volumes of meltwater entered the ocean. The redistribution of planetary mass that followed was large enough to affect the moment of inertia, and therefore the rotation rate. The crust, freed from the weight of the ice, began the slow upward rebound that continues to this day in Scandinavia and northern Canada. The overall picture, mass leaving the poles, crust adjusting, rotation responding, is the same physical story playing out now, but driven by different causes at a different pace. The geological record of that transition reveals something important about how these mass redistribution events actually unfold. They are not smooth or gradual. They are episodic. Different ice sheets collapse in different sequences. Meltwater enters the ocean in pulses rather than as a steady flow. The solid Earth responds with its own delays and rebounds, each with its own timescale. Meltwater Pulse 1A, roughly 14,500 years ago, raised global sea levels by somewhere between 14 and 18 meters in a span of 3 to 500 years. The redistribution of that volume of water in that short a time produced changes in the planet's moment of inertia large enough to leave detectable signatures in rotation models. The event was not predicted before it happened. It was recognized only after the fact in sediment cores and coastal stratigraphy. Nothing in the steady accumulation of data before that pulse announced it was coming. The volcanic record adds another layer. Periods of rapid deglaciation are associated with increased volcanic activity, and the mechanism is pressure release. Ice sheets exert enormous weight on the crust beneath them. When that weight is removed, crustal pressure drops, and rock in the upper mantle that was already close to its melting point, held there by a combination of heat and pressure, becomes more likely to melt and rise. Iceland is one of the most studied examples of this effect. Research on Icelandic volcanic history shows elevated eruption rates during and after the last deglaciation, with a lag of centuries between ice removal and volcanic response as the crust adjusted to the changed load. Early monitoring data from Iceland, from Greenland's peripheral volcanic zones, and from West Antarctica suggests subtle changes in subsurface pressure and seismic activity that are consistent with the beginning of a deglaciation-driven volcanic response. That response has its own timeline, measured in centuries, but it has its own potential to interact with the rotation system through the redistribution of volcanic material across the crust and the changes it produces in the moment of inertia. The connection between Earth's rotation rate and earthquake activity sounds like the kind of speculative claim that circulates in popular science coverage without much foundation. In this case, it is not speculative. In 2017, a paper published in a geophysical journal reported the results of an analysis of historical earthquake data spanning more than a century. The researchers found that periods when Earth's rotation slowed slightly were followed, roughly 5 years later, by increases in the frequency of major earthquakes, those measuring magnitude 7 or above. The correlation was statistically significant, and the proposed mechanism was physically grounded rather than coincidental. When Earth's rotation slows, even fractionally, the equatorial bulge adjusts. The planet is not a perfect sphere. It bulges outward at the equator because of centrifugal effects from the rotation. When the rotation slows, the bulge decreases slightly, and the crust at lower latitudes shifts inward. That movement applies horizontal stress to tectonic plates. Faults that were already close to failure, already loaded with the accumulated stress of decades of plate movement, can be nudged past their threshold by the additional pressure. The logic runs in reverse. When the rotation speeds up, the equatorial bulge increases slightly. The crust at the equator is stretched outward. Faults under tension rather than compression can be triggered. The type of earthquakes most likely to be influenced differs, but the mechanism is the same: rotational change applying stress to a crust that is already under pressure from tectonic forces, and that additional stress determining which faults fail first. The paper noted that at the time of writing, the planet had recently exited a period of slowing and entered one of acceleration. By the logic of their correlation model, the mid-2020s would be a period worth watching. That prediction has not been proven or disproven definitively, and most seismologists are appropriately cautious about earthquake prediction of any kind. The correlation is real, but establishing causation requires a mechanistic understanding that is still being worked out. What is less contested is the connection to volcanic activity. Rotational changes affect the behavior of partially molten material in the upper mantle in regions where rock is close to its melting point. Changes in rotational stress can affect where and how that material migrates. Studies examining global volcanic eruption rates over the past several centuries have found a weak but detectable correlation between periods of rotation anomaly and subsequent volcanic episodes, again with a lag of years to decades between the rotational signal and the surface response. The lag matters because it means the effects of the current acceleration may not be fully expressed yet. Whatever the surface rotation is doing to faults and volcanic systems, the response is still traveling through the geological system, arriving in episodes that will not all be attributable or even linkable to the rotational changes that preceded them. This is part of what makes the current situation difficult to communicate without either understating the science or veering into alarmism. The planet is under more simultaneous stress right now than at any point in the modern instrumental record, and the systems involved are connected to each other in ways that make the combined response less predictable than any individual component in isolation. In physics classrooms and research institutes, there is a term for what happens when a system is driven simultaneously by multiple forces that are themselves connected to each other through feedback loops. The system becomes non-stationary. Its statistical properties, its average behavior, its range of variation are no longer constant. The historical record becomes a less reliable guide to future behavior because the conditions producing the history are no longer the conditions now in play. Earth's coupled geophysical systems are now in this regime. Consider what is happening simultaneously. The rotation is accelerating beyond any measurement in the modern instrumental record. The inner core has changed its rotational behavior. The outer core's circulation pattern has shifted, producing both a rotation signal and a magnetic field signal. The magnetic field is weakening regionally in a pattern consistent with early excursion behavior, while the global field has declined by nearly 10% over the past century and a half. The ice sheets are losing mass at rates that were not projected to occur until later in this century under median climate models. The meltwater redistribution is shifting the planetary axis and altering the moment of inertia in real time. The oceans are warming, expanding, and changing their deep circulation. The atmosphere is responding to all of the above and feeding its own angular momentum changes back into the rotation. Subsurface pressure changes in deglaciated regions are consistent with the early stages of a volcanic and tectonic response. Each of these is documented independently. Each has its own body of peer-reviewed literature. Each is being monitored by separate scientific communities with separate funding streams and separate publication venues. What is less common is the attempt to look at all of them together, in the same frame, at the same time. When researchers have done that, what they find is that these changes are not independent. They are physically coupled. The weakening magnetic field reflects outer core changes that also affect rotation. Ice loss affects both rotation and ocean circulation, which in turn affects the magnetic field's excitation pattern. Atmospheric shifts affect rotation and also affect precipitation patterns, which affect ice accumulation rates. These are not metaphorical connections. They are physical couplings with measurable signatures in the data. The result is a system moving in multiple dimensions simultaneously, where the movement in each dimension amplifies the movement in others. A figure skater who is pulling in their arms, while their center of mass shifts, while someone is blowing on them, the combined effect is not simply the sum of the parts. It is a system responding to all of those things at once, in ways that depend on their relative timing and interaction. 3 independent research teams have attempted to build models that incorporate core dynamics, ice redistribution, ocean circulation, and atmospheric angular momentum simultaneously. Their conclusions overlap in some areas and diverge significantly in others. All 3 models agree on one thing: whatever comes next, the planet will not simply return to where it was. The question is what kind of new equilibrium it is moving toward and how long the transition takes. In 2017, researchers analyzing the independently measured data streams from each of the major systems described in this story did something that is not common in the fragmented world of geoscience. They mapped them all onto the same timeline. Core rotation anomaly data referenced against the 1990s baseline showed a clear departure beginning around 2009 to 2010. Outer core angular momentum estimates derived from magnetic field change rates showed a concurrent shift in roughly the same window. Surface rotation data showed the acceleration beginning to emerge from background noise around 2016. With the most extreme values appearing between 2020 and 2022. Greenland ice mass loss rates showed a step change increase beginning around 2012 and continuing to steepen. The South Atlantic anomaly's minimum field intensity showed a consistent decline with a steeper gradient emerging in the mid-2010s. Arctic sea ice extent showed its sharpest multi-year decline beginning around 2012. Atlantic circulation strength estimates showed accelerating weakening in the mid-2010s. 7 independent geophysical systems, measured by different instruments, maintained by different institutions, published in different journals, each showing its major departure from its historical baseline in roughly the same decade, long window centered on approximately 2010 to 2020. This convergence is not a constructed narrative, it is what the data shows. The probability that 7 independent systems all departed from historical baselines within the same decade by coincidence, with no shared physical driver, is not zero, but it is very small. What the convergence suggests is that these systems share a common excitation. Something changed in the coupled Earth system during that window in a way that propagated across multiple layers simultaneously. Whether that something was primarily the inner core, primarily the ice-atmosphere system, or primarily the magnetic transition, the effect was system-wide, and system-wide changes in Earth's coupled geophysical behavior do not stabilize quickly. The geological record shows that when multiple systems enter a departure phase together, they tend to remain in that departure for decades to centuries before settling into a new equilibrium. And the equilibrium at the end is not identical to the one at the beginning. This is perhaps the most consequential sentence in this entire story. The planet is not broken. It is not heading toward extinction, but it is in transition. And the infrastructure of human civilization was not built for transitions. It was built for stability, the remarkable geophysical stability of the last 10,000 years, a period that by geological standards was extraordinarily calm. Every city built at a specific coastal elevation, every satellite calibrated to a specific rotation rate, every power grid synchronized to a specific timekeeping standard. All of it was designed for a planet that is no longer behaving in the way those designs assumed. And 3 theoretical frameworks compete in the research literature to explain what is currently driving the surface acceleration, and they are not mutually exclusive. The first is the core-driven model, which holds that the primary driver is the change in inner core rotation and its effect on outer core circulation. In this view, the inner core reversal, or at minimum its dramatic deceleration, transferred angular momentum upward through the layers, and the surface acceleration is the delayed arrival of that energy at the crust. The prediction from this framework is that the acceleration will continue until the angular momentum transfer is complete, then stabilize or reverse as the system finds a new equilibrium. The timescale is estimated at decades. If the inner core continues to shed angular momentum, the surface keeps accelerating. If it has already reached a new stable rotation rate, the effect will eventually dissipate. The second framework centers on ice and atmosphere coupling. In this view, the dominant driver is the combination of polar ice loss and its effect on atmospheric circulation, specifically, the weakening of the temperature gradient between the Arctic and mid-latitudes that drives the jet stream. A weaker, more meandering jet stream redistributes atmospheric angular momentum differently than a strong, tightly banded one. The result is a surface rotation rate that tracks the trajectory of Arctic warming, continuing as long as ice loss continues and potentially intensifying as feedbacks between sea ice loss and atmospheric circulation strengthen further. The core dynamics are real in this model but secondary, a contributing factor rather than the primary cause. The third framework is the most speculative, but not without physical basis. It holds that the weakening magnetic field, particularly the changes happening in the outer core, beneath the South Atlantic, is altering the electromagnetic coupling between the outer core and the mantle. A weaker coupling means less rotational resistance between the layers, allowing angular momentum to transfer from core to mantle more efficiently. The result is a transient speed-up of the surface, a symptom of a magnetic transition that may be the early stages of an excursion or even a full reversal. In this model, The surface acceleration will continue and potentially intensify as the coupling weakens further, then reverse dramatically when the field begins to recover. Each of these models has published support and published critiques. None has been falsified. What all three share is the recognition that the current situation is not a random fluctuation. There is a physical story being told in the data. The debate is about which chapter is primary. The honest answer from the researchers closest to the data is that the three frameworks are probably all partially correct. The core dynamics are real and appear to be contributing. The ice-atmosphere coupling is real and quantifiable. The magnetic field changes are real and physically linked to the rotation through the outer core. The combined effect is a planet that is simultaneously being pushed faster by several mechanisms at once, with different time scales and different trajectories. What happens next depends on which of those mechanisms dominates in the coming decades, and that is genuinely unknown. The practical consequences of all of this are not abstract. They are already showing up in the systems that people depend on daily. And the engineers maintaining those systems are working harder than they were a decade ago to keep up. Every commercial aircraft flying today navigates using a combination of satellite positioning, inertial reference systems, and radio navigation aids, all synchronized to coordinated universal time. When a flight crosses an ocean, the navigation computers have been tracking position continuously against a model of Earth's orientation in space. Any inaccuracy in that model propagates into position error. Modern precision approach procedures, the ones that guide aircraft to within meters of a runway in zero visibility, depend on satellite positioning systems whose accuracy depends on Earth rotating predictably. Aviation safety authorities have issued technical bulletins acknowledging that geomagnetic and rotational anomalies require more frequent updates to navigation databases than the historical 28-day cycle assumed. Power grids operate on alternating current at a fixed frequency, 50 cycles per second in most of the world, 60 in North America. Grid operators use time synchronization to coordinate the phase of current across interconnected systems spanning thousands of miles. When sections of a grid run slightly out of phase, energy does not transfer efficiently across the connection between them, and protective systems may disconnect those sections to prevent equipment damage. Those protective systems are calibrated to thresholds established by decades of operating experience under conditions where timekeeping was stable. Technical analyses published by grid operators in Europe and North America have both concluded that existing protective systems are adequate for the current level of anomaly, but would require recalibration if the anomaly grew significantly. The current anomaly has been growing for almost a decade. Hospital systems are perhaps the least obvious application and possibly one of the most serious. Medication dispensing systems record timestamps on every dose. Operating room monitoring equipment records data against synchronized timestamps that constitute the legal medical record. Linear accelerators used in cancer treatment coordinate beam delivery with patient breathing cycles using precise timing. In each of these applications, a discontinuity in the timekeeping signal, even a 1-second gap, does not just create a data anomaly. It creates a gap in the medical record that triggers automatic safety alerts and, in some implementations, automatic system shutdowns pending manual review. Hospital IT teams have been aware of this problem since at least the 2012 leap-second crash that affected dozens of major platforms simultaneously. Most have implemented mitigations, but mitigation is not the same as elimination, and the resources spent managing timekeeping uncertainty are resources not available for other improvements. There is also a coordination problem that operates across all of these domains. The engineers maintaining aviation navigation systems, the teams managing power grid synchronization, the IT staff handling hospital timekeeping. They are each aware of the challenges specific to their domain. What fewer of them have full visibility into is the aggregate picture. The same underlying planetary change is driving stress in all of their systems simultaneously. And the mechanisms producing that stress are themselves interconnected in ways that make simple predictions unreliable. A change in core dynamics that accelerates the rotation also weakens the magnetic field. A weakening field increases radiation exposure for satellites, which introduces errors in the navigation systems that aviation and maritime industries depend on. Ice loss that shifts the axis requires updates to navigation databases and timekeeping parameters. The challenges are not isolated technical problems with isolated technical solutions. They are symptoms of a single planetary transition. Everything described in this story is measured. None of it is modeled extrapolation or speculative projection. Earth is rotating faster than at any point in 50 years of precise observation. The inner core has changed its behavior. The outer core's circulation has shifted, leaving signatures in both the rotation data and the magnetic field data. The magnetic field is weakening regionally and globally. The ice sheets are losing mass at rates that were not expected until later this century. The meltwater redistribution is shifting the planetary axis and altering the moment of inertia in real time. The ocean circulation is weakening. The atmosphere is responding to all of the above and feeding changes back into the rotation. Subsurface pressure changes in deglaciated regions are consistent with the early stages of volcanic and tectonic response. 7 independent systems, measured by 7 independent monitoring networks, departed from their historical baselines in roughly the same decade. That is what the instruments say. What comes next is where the certainty ends and the genuine scientific uncertainty begins. The planet is not broken. It has been through transitions far more extreme than this one across hundreds of millions of years of geological history. Life has survived all of them. But human civilization was not built to be tested by planetary transitions. It was built during 10,000 years of unusual stability, unusual by geological standards, the kind of quiet interlude that comes between ice ages and geomagnetic upheavals and episodes of rapid polar drift. The cities at the coast, the satellites in orbit, the power grids spanning continents, the navigation systems guiding aircraft to precise runway thresholds in zero visibility. All of it was designed for a planet that behaved within a narrow and familiar range. That range is no longer the operating environment. There are 2 broad scenarios that researchers consider. In the first, the multiple systems that have simultaneously departed from their baselines are near a natural turning point. The inner core's angular momentum transfer completes and the surface acceleration stabilizes. The jet stream finds a new configuration that partially compensates for Arctic warming. The magnetic field recovers from its current weak phase, without completing a reversal. The ice loss rate is slowed by changing precipitation patterns or political responses. The system reaches a new equilibrium within a generation, and the engineering challenges, while significant, are finite and manageable. In the second scenario, the coupled feedbacks continue to amplify. Ice loss accelerates further, the jet stream weakens further, the magnetic field continues to decline, and the combined effect on rotation and infrastructure grows faster than the institutions maintaining those systems can adapt. The systems with the least redundancy fail first, and their failures stress the systems connected to them. Neither outcome is inevitable. The uncertainty is not false modesty or performative caution. It is real, and it is larger than it was a decade ago. More monitoring has produced more evidence of change. Better models have produced better resolution of the mechanisms. And better resolution has revealed how tightly the systems are coupled, which means how much a change in one can drive changes in others. The researchers watching all of this most closely do not use the word catastrophe. They use the word transition, a transition between stable states, with a gap in between where the behavior of the system is harder to predict than in either state it is moving between. The transition is already underway. The instruments are running. The data is arriving continuously. And at the center of it all, the planet you are standing on is rotating faster than it has in half a century. Driven by forces that reach from the ice at the poles to the iron at the center, and the full story of where it is going is still being written in real time.